So practical exercise is about activity 12 package, and if you like, we can do some preparations, maybe useful for monitoring purposes. For example, graphical monitor for system activities and resources, which is quite slow and heavy but feature rich, called GNOME System Monitor. So where is the difference between this top in terminal? In terminal, with stop command you can't see very exactly what is history of currently used resources, like in this graph. Top shows some tendencies how system load is changing in some way, which is for example used in many ways in statistics, like in COVID cases and COVID deaths or whatever. It shows average for load in 3 different spans of time. Last few seconds, I do not know precisely, like 5 seconds or whatever, then last minute, and then I think last 5 minutes. And what can you find out from such averages, which are averaged in shorter and longer time? Of course, averages for shorter time are changing more rapidly, and averages in longer time are changing more slowly. But if you see that, for example, average of shorter time is larger than average for longer time, for example, for longer time it is, let's say, 10, and here you see 20, you can understand that it is increasing recently. If this average in shorter time is smaller than in longer time, you can understand and deduct from that that load is decreasing recently. And so from these 3 numbers, larger amount of time, little bit smaller, and even smaller, you can see, for example, what is latest tendencies about system load. And from this I can see that recently load of system is decreasing, because from previous time, for longer average time, these numbers are bigger than here. And now more specific details about numbers themselves. Numbers themselves here may be very important. For example, where we see these numbers of load average may happen to appear in many other GNU utilities in command line, like in uptime, which shows how much time system has been up, how many users, and what is load average, and again last few seconds, last minute, and last 5 minutes. And what can you say about this? These numbers, if to talk very specifically, is average number of processes waiting for immediate execution. So that if that would be Java thread, that would be in this runnable state. So it is waiting for execution, but not executed yet. and this is average number. For example, for some very small fractional amount of time, there may be one particular process waiting for execution, but then it's starting executing, it's not into this queue anymore, so it's executing and it becomes 0 again. And what this means that if it's smaller than 0, smaller than 1, it means that mostly there are now waiting threads which are waiting, ready for execution, should be executed, but are not executed because system load is heavy and it's busy and it cannot execute so many processes as they may be needed for execution. So anything smaller than 1 is good. Everything which is close to 0 is very good. So this means, of course, very good if you want to have spare capacity and spare power to be used when this is really needed. If you, for example, need to pay for some remote virtual machine in Google Cloud or Amazon Cloud or Microsoft Cloud or whatever, then this means maybe you are paying too much for too large instance because it's not very heavily used. When this number becomes larger than 1, this means you have at least some of these processes waiting for immediate execution, and that means your responsivity of your system becomes worse and worse and worse, because when you add some new task for it or new process for execution to it, then it will not be executed immediately, so you will need to wait. And if I have physical 4 processors on my computer, maybe nothing very bad will happen if this load average will go up to 4, approximately. But after that, if it will be larger than that, then this system will not be responsive anymore. It will work like a busy worker in some enterprise. You will have just longer and longer queue for execution, and it will execute as quick as possible. It will not be quick enough for quick response times. And then your system switch from, let's say, interactive mode to batch mode. In interactive mode, you can always expect that if you create some request, you will get response, if not immediately, then pretty quickly. If it is working in batch mode, so this load average is bigger than number of physical processors, you will create a request and you will just wait who knows how long time until this response will be ready. And then if this number is bigger than number of processors, then you need to check what actually happens with tendency, because usually what happens is that if system starts working in batch mode and you add more and more requests to it, then it may just be overload because it may not have enough virtual memory, it may not have enough other things, and this load may increase and your computer hangs up, and then you need to restart it. So that's about these things. But here you can see graphically as a percent of processor time, and if these are mostly idle doing nothing, then you have spare capacity to do something else. So that's about monitoring. Then what also may be important, as soon as you start creating multi-threaded applications, Eclipse may get confused, or IntelliJ IDEA or whatever, about how many processes are running as a child processes for this one they may not be killed properly, you should know at least one option for kill. And here, old school program is just kill. And for kill you need to set process ID to be killed. And -9 means kill forcefully, do not ask any questions, do not wait, etc. And here, like PID. But for Linux particularly, which is more elegant than old school Unix, there is also command kill all. And this works differently. Instead of process ID, here you can write pattern. And if this pattern is like Java, then you will kill all processes which have Java in their description. For example, here are my processes which contains word Java in their description, and this is only one process. As you can see, it is my Eclipse, and if I say kill all -9 containing Java in process description, then I can kill my Eclipse. And of course, when you do this, if there was some opened files which were still edited, you open this Eclipse and your project looks like broken. Eclipse doesn't know how to compile it, etc. So it may be that some of metadata are broken. So therefore it's always recommended, as I do, don't have opened and saved files. And unsaved files in Eclipse are like with star with the name, so such ones. You should always have everything clean, no stars here, everything saved. Otherwise, if you will kill it forcefully, something may be broken and then you need to restore your working environment. So that's about preparation. Now about business. Business is following that if we open this picture, let's open it with external programs. Okay, let's open it in this. Here we see 3 sequence diagrams. How does it work? Our task here is to fill up this array of integers with pseudo-random numbers. And we have to fill it up in 3 different ways. First, we set up this array in stupid approach, in sequential approach, and parallel approach. How does it look like in sequence diagram? So time is flowing here from top to bottom. And if fill stupidly method is called for this array filler manager, we fill up this array with pseudo-random integers in the following way. That we have loop for each particular cell for this array, and we call array filler, which will be doing actual filling procedure. But to fill it up, we have to emulate this latency time, like waiting for network to send data, waiting for disk to be ready, or whatever this process is which takes some time to do it. So I always need to wait this specified amount of time to fill up one particular cell inside this array. And why it's called fill stupidly? Because you will see that because of these latencies involved, that for each particular cell which can be filled up, you need to wait specified amount of time. It will work very slowly, because most of the time you will see that you are waiting for this timeout to happen when you can fill up one particular array cell inside this array. Then in second approach we are allowed to do so-called buffered writing. And we can call this array failure only once, and we still need to wait specified amount of time for this emulated latency. But then we can fill up all these cells from the first cell till the last cell all at once. And we will see that it's something like from unbuffered writing or stupid writing and buffered writing, that here performance increase is approximately 1,000 times. Why 1,000 times? Because latencies involved here are approximately a few milliseconds, and 1 mil is 1,000th of a second. So if you wait just once and then fill up many thousands of cells here all at once, like for buffered writing, this improvement is approximately so. If latencies are bigger and the amount of data is bigger, then of course this improvement from like stupid unbuffered writing and buffered writing may be even more than many thousand times. And then in third option we will have to improve this performance a little bit more. Again, we will have to write these pseudo-random numbers concurrently in separate threads of execution. And minimum amount probably is 4, because on my computer I have 4 physical processors. You may try to check how it works with more than 4. And so they do this buffered writing. Each of these threads of execution need to wait specified amount of time, but then they can write all these data or numbers in this array from the beginning till to the end for each particular part of this array. And of course, to make it faster, each of these threads of execution needs to fill up their own part of array, because if they will be overwrite the same part of array, they will just overdo the same amount of work without any improvements. And you will see here that here you are lucky if you get improvement approximately 2 times because of these management overheads. While you prepare for these threads, start executing, then of course you need to wait while these threads are finishing. Otherwise you will not be sure that this array is actually filled up. And so you will see this Amdahl's law here in practice, that you can't get it 4 times faster if your preparation and finalization takes considerable amount of time. If that array would be very, very large, like gigabytes of data, and this preparation would take just few milliseconds to prepare and start and to finalize here, then you would be very close to 4 times. Better because we have 4 processors, but because of these management overheads at the beginning and at the end of these, in this particular case we will see that improvement for just 2 times is pretty much what we can get there. So, is business what we need to do here is understood? I don't hear any complaints, so as usual probably we can start implementing independent class, and now both classes are a little bit dependent, so in implementation of array filler depends on array filler manager, because this array is located inside this class. And these are just like workers which need to do fill up these cells of that random of that array. So what is already given to us here? Static import is given to us to this array. That means we can always return to just simple name array. We need to do something about it. What can we do about it? Okay, we can check lengths for it. And when we do this, we see that this short name actually refers to this variable here in array filler manager. So that is what is good about static imports, that you can create as a local shorthand short names to refer to some other variable somewhere else. Otherwise, we would also always need to write. Without static import, we always would be required to write it in ceremonial way. Class and its static structure, class static structure. But with static import, we can shorten it in following way, so we know that this short variable name refers to this variable in this class. So what we need to do, first we need to implement two constructors, and in this constructor, when this array filler is called, we need to call another constructor as, then we will start implementing this one first, and we need to save passed values. I think that is what is required here. And in this, call another constructor. Okay, let's call another constructor. And fill missing values from beginning till to the end of an array. So that means latency is given as it is, start, and from beginning of the array is 0 cell, and end of an array is array length -1. And we hope here that this array will never be 0 length. So as usual here, we are not paying too much attention about robustness and edge cases for errors. We just want to implement it if everything is right. Now what we see here is that array filler implements runnable interface. So that means it has to override its run method or implement. And override is just a way how to say it for compiler. And when invoked, we need to sleep for given latency. And when we do this, exception may be thrown, and therefore we need to surround it with try and catch. Because nothing here is told that we are allowed to throw exceptions. So here we are emulating this latency time when nothing happens because of different reasons. And then, when this filler has waited enough amount of time, we need to do what? We need to say array starting from prompt to 2, so we need some cycle for from, I think, increase. This is wrong order. This is condition and this is what we need to do. This cell of array should be some value and this is random value. First we need to initialize. Do we have? We have random variable declared for us, so we need to initialize it. Start value is this, but array cell for us is I. What is wrong here? New keyword is missing here. And then so what is happening here? A random object is object where you can generate pseudo random numbers. And one of things you can initialize it is just new random. And in this case, you will start with some unknown settings, because in this case, pseudo random number means that it always gets next random number, integer, floating or whatever, with determinate algorithm. So this looks like random numbers, but they are not. They are in strong sequence, each after other. But if we initialize random number without any parameters at all, then it takes initial so-called seed for these pseudo-random numbers from the state of our system. I do not know what it takes in account, like values of registers in some processor, maybe temperature in cores or whatever. So it takes many different parameters together about your system, somehow mixes it together with some hash function and gets some initial seed like blah 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 random number. But if we add this seed as a determinate value, and let's do it a few times. For example, if we initialize it without initial seed, we see that all these numbers look like random numbers, even though This number depends on that number, this number depends on that number, this number depends on that, and this depends on that. But if we say that initial seed is one fixed value here, then we can rerun it 1,000 of times and we see that all these pseudo-random numbers are always absolutely the same. So that means these look like a random number, but this sequence of these numbers will be always absolutely the same, because it will start with this particular seed. And what is happening here is that we have to pass initial seed, which depends on passed start value here to this filler, and cell number inside this particular array. And then when we fill it up, then it will look like a random number, but actually it will be strongly determined, because it is something like hash function. You get different number for sum of these two numbers, and then it can be checked that it is filled up correctly. And with this one, I think filler itself is completed. Now we can implement this container class, which uses array fillers to fill up this array. First thing, we need to do some preparation. We need to save these values for later use. So and these are all static structures, so they belong to the class. So we have to say that number of array filler number. Array size is not remembered, but I need to initialize array. Initial. It here. Just need to read. So you know that there are only two different kind of documentations. Either documentation is too little, or documentation is too much to read. But and then what we return reference to initial array, so we return this array. And here again, because array is not clashing, this name of this variable is not clashing with passed parameters for method, here I could also say it in a such way, but if I want to be ceremonial or do it with see some pattern here, so here I'm not consistent. Ceremonial reference to static structure in this row and non-ceremonial reference to static structure in this way. If you want to be consistent, you can do something like this as well. And now we have to implement these three different filling algorithms. First is fill stupidly, which is this unbuffered simulation of unbuffered writing. You send only one number to the array to fill up, and you always need to wait for required amount of time to fill up only one single cell of array. So to fill up entire array we need to do some kind of loop. We can start with 0, I think. We could be, because arrays are 0 indexed one cell less than its size, equals plus, yeah. And then what we need to do, we need to create new array filler object. And we have to say that it needs to fill up only one particular cell. How do we say it to it? It is this constructor, I think. And of course, when we use this method, we need to remove types here, because and from and to is actually E and E. And then we need to invoke it, but not in separate thread, but in the same thread. So that means we call its run method directly here. And I think that Fill Stupidly looks like it's implemented. And if we are optimist, we may try to run JUnit test for it and see what happens. Unfortunately, everything fails here. That's interesting. Why nothing passed even for fill values stupidly? Let's have a check. So we wait as it required. Fill it from prompt to 2 cells with pseudo random number value. What can we do here to test it out? Thank you, Jānis. So we start from cell 0. No, that length is larger than. Yeah. So if its length is 1, then cell is only 0. It's smaller than, yeah. Because it's smaller than, yeah, you are right. Thank you very much. So I think that's a problem. As you can see, I usually write cycles with precision ±1. Yeah, and now it even passes. Thank you very much. So either I have to write it either length smaller than and equals -1, or because I'm using just smaller than, it is just array length here. Yeah, that was my mistake. And so we have, with help with your classmates, implemented this first method when we fill up each particular cell stupidly because it takes. And here this warning, you may ignore it, may not, depends, because it says that there are many Java processes. I think this is problem, because I have opened this image which also contains Java inside its description, blah 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 blah. So I got this warning here that I have two processes which contains Java inside it as a string in its description. But because I know that this other process is actually image viewer for this file here, I may ignore it. It is just a warning. But you may not ignore it if you have actually some undead zombie processes running from your previous failed attempts or these experiments. So next thing we need to implement is emulation or simulation of buffered writing. We still need to wait required amount of time, but then we are allowed to fill up entire array from the beginning till to the end. That means that here, from manager perspective, we don't need to have any cycle, because we have do everything at once. And here, what can we do? Okay, we can reuse this constructor now here, which does this calculation here already. So if we have calculated that from zeros L to, and this I think is done properly, I think so. Then we can pass only these variables here, fill a run, and everything should be going now from zeros cell till to the last cell, because that's how we set it here for this constructor. And we can test it out. And it even works. I don't like this particular failed subtest, but maybe it depends on some of these other tests here as well, because as far as I can tell, I have implemented required sleeping here before actual execution. So I will ignore this for now. It is just a warning for me. And now we have to do it concurrently. And here the biggest headaches for these who are poor at arithmetics is to split up this task for fillers in approximately 4 or 8 or 16 different parts. don't know about you, but here in Pārogre, finally we got some raining. That's nice, at least sometimes, when there is too much of heat and dry weather. So, yeah, where was I? So we need to split up this array in several equal parts. So here would be number of cells for this array, starting from, let's say, 0. And if we have something like small n of runners or these fillers, and if it's, let's say, 4, we need to split it up in 4 different parts, and each of them, of course, runs concurrently to fill up their own particular part. And how can we do this? We need to know what is range here for each particular of these fillers. And then we do something like this. We set up first array with its range, then for next filler we say range plus range again, then range plus range again, then range plus range again. And again here we can do it with precision plus minus 1. It shouldn't be very good if we would overwrite one particular cell with one thread at the end and another thread at the beginning, but nothing very bad will happen. And here we will need to check that because of integer arithmetics we need to ensure that we actually go till to the end here. Other thing, how can you do this? You could implement it in different way, that each of fillers jumps number of these fillers in ahead. So first filler fills up cells like 0, 3, 7, blah blah blah. Next filler fills up cells 1, 4, 8, blah blah blah, and then it jumps. But it's not recommended way, because increment plus plus works at least twice as fast as like plus 1. Because here you need to store 2 values, current value, another value. For processors there is no difference, is this one just 1 or 55,000, and then it needs to write it back into this initial value. But with increment it just directly adds plus 1 to this value which is stored in register of processor. So therefore we will not do this approach, that they are interleaving each other in shifted way by this step, but we will do it more properly, even though it's a little bit harder. So we need to have something like integer let's call it count. Oh, okay, let's call it count. And let's say it initially to 4, then we will experiment with something else. Then we need to check what range is, and we can do something like and of course we assume that thread count is small and length of array is big. Because this is integer, that is integer, and remember, when we divide integer by integer, it is rounded up to the next closest integer. So we assume that length is much larger than thread count. Otherwise it will be rounded down to 0 and nothing will work for us. And then we need to prepare to prepare these separate threads for running. What we need to do here, we need to create separate array fillers, but we will need to join them because at the end we start concurrent parallel execution, but at the end we still need to wait and to be sure that all these parts in concurrent threads are filled up properly. We can't just say everything is done, because then this array will actually not be filled properly yet. And I think we have design given to us here. We can remember all these threads in static linked list with these threads. So what do we do? First we need to create one particular array filler. Yeah. And we need to give following information to it. Latency is easy, start value is easy. This is not so easy. So we will do something like that. From is initially from is 0. And I think it will clash with what we have here. No. And then int2 is range initially. And then that would be for first particular step. And then we need to increase these froms and to. So what is from? From becomes what was 2 before that. But I think we can safely also say we can shift it +1 here. And 2 is 2 plus range. What do you think? I think it should work. So we have from range, then from becomes what was 2 after that, and 2 is another range here. And then we need to remember references to this, and we need to run it as a concurrent thread. So currently I have created only my array filler, but it will not work independently if, for example, I will directly call its run method. So because this array filler implements runnable interface, we need to create a thread object first, because without creation of thread object, this concurrent execution will not happen. So we have this particular case that our class implements runnable, and to run it concurrently we have to create new thread, pass constructed object to it, and only then we can call start method for it. So we need to do something like this. And of course you need to type it correctly, and instead of hello runnable, we have created filler here already. We put it here. And then we need to remember reference to this thread, because we will need to join it or to check that it has completed. And for that, what do we need? First, we have to initialize this linked list of threads. And I think we need to add this type parameter here as well. And then we can say thread, let's add this thread. And either here or there we can say then start. And so you see how much of management we have to do here. And this is about starting. And after that, something is wrong here. Then we need to join. So here we had, let's say, and here, because I don't need to have index, my decision is following. If I need to refer to something by index, then I do this C-like for. If I don't need index, I can do this iterator for threads. So what is wrong here? I think nothing wrong. And again it may throw some kind of exception here. We need to catch it and handle it. And because here is quite a lot of code, of course I'm not absolutely sure that I have implemented them correctly. And we may test them. And what we will do is following. First, let's say we will print out. Okay. What is our thread count for debugging purposes? And then here we'll print out range. And here for particular step we will print out from. Oh, it even passed. I'm gladly surprised. But even though it passed, you see, we have exceptions. Array index out of bounds exception, index 100 out of bounds for length 100. So why do we have it? Because of rounding errors. So here for this last figure from and to should be 76 till to 99. But I have 100. How can we adjust it? I think we will just patch it. If he is last one, so this, if he is and do I use E somewhere else besides this? No, then I will start with 1 and 1 unequals, and if it is equal to thread count, then 2 is array length minus 1. Doesn't look good, but should work. Or you can do it differently. If 2 is larger than array length minus 1, then reset it to a little bit smaller one. I don't know which is better. Both are ugly patches for your logic and these rounding errors, but both should work in similar fashion. So it still works, but we have again array index out of bounds exception. We also need to print out what the sizes of our array before that. Array size 100. Wrong is something is wrong with my logic here. It's still 100. Yeah, so I think this should be working, but if it doesn't work, we patch it in different way. We say 2 is 2 plus range. I do something like if 2 is larger than minus 1, 2 is length minus 1. And now for array size 100 we get 99. That's nice. So what do I see? I see array.length in many times in my code, and that means that particularly either in this method or I will introduce another variable here. because if I need to refer to it in many times, and it's just and then I can make it nicer here, nicer here, and nicer here. And even so it works here, I am still thinking about this patch. In most of cases what we see here with this rounding error is integer. When we add range, our range ends up outside of array, so we need to make it smaller. But there may be cases when we calculate this range and add it range many times, and we end up somewhere here, and we actually need to increase it to fill up everything till to the end. And to check how it actually is working, let's make this thread count much bigger. And we see that now we have a problem. Wrong cell value expected such number, but we got 0. Why? Because now for particular array, so what is array size? Array size is 100. But we have ended up with only 96 here, and that is not good, and therefore even this worked for us pretty well with smaller amount of these particular threads. Now my calculation, so rounding error is now going in opposite direction. And therefore I will revert it to what I was wanted to do is if E is this thread count, only problem is what I did wrong there. Why it didn't work? I think that's correct, because it's last one for E should be, okay, we can print it off. Check that it is, finally it is 16, not 15. Yeah, it is 16, but it is still 96. Ah. What I forgot here is that 2 is... I did do it 2 plus range here, so why it didn't work for me? That's something strange, -8. And now it works, and I'm surprised. Because, for E15 we get this range here. Why it's so? We start with 1. Because these initial statements here, that my e equals 0. Yeah, now I understood. Okay, so this is more robust solution because now we have solved this for both types of rounding errors. If it's too small for last this array filler, we increase it. If it's too big, we decrease it so that it always ends up in last cell of an array. So can we put it here? So we can make it less ugly, set both to 0, and these do you like this approach, that this is 0 now and we increase this to before that? And then I think we can get rid of this -1 here. Still looks a little bit ugly. And then of course we need put everything for patching here before that. So we got rid of this little bit ugly condition here, -1, and here we set it initially to zeros and we calculate it always inside this loop. That is good. What is not so good is that this first range part, or actually is calculated before filling up and after is after that. But if you count characters, lines of code are still the same, but if you count characters, it becomes a little bit shorter. And so I will leave it somewhere here. And when it works, we can get rid of all these debugging things, because these are not needed anymore. And now we can check performance, how well it works for 16. We still have one output which makes everything slower. And here also what you need to remember is that every time you print something in standard output, there is only one output here in console you can print. If you have multiple threads printing something out, then they will be implicitly synchronized, because they will wait for Q here to print out something here, and everything will work much slower. So for different kind of real-time processes, adding debugging may change very radically how your implementation, your solution works. And so we can see now general statistics, stupid processing, 700 cells per second, sequential processing, few 24 million cells per second. You see improvement is 32,000. And parallel processing 43 million cells per second, improvement only 1.8 times. Let's make this number smaller, then we will probably have less management overhead. Maybe we can improve it. And of course we could run it several times to check some averages there. See, I made it less complicated and my performance actually improved. and if we make it, let's say 4, .3, let's run it. Only 2. I think something like 8 threads on 4 physical processors may be better. Why it happens so that adding more threads actually improves it? Because it adds complexity. Here you should know something about arms race. Arms race between different applications. So here is your lifeline of your CPU, and here are these slices of time. Let's say initially they are all equal for different processes or threads inside your application or whatever. And system scheduler in operating system initially works in more or less fair approach that each of these processes and threads get equal share of time. But if some of these applications wants to be better than other, it may artificially add more threads, like Google Chromium is doing it all the time. More threads than it actually needs, and that means that if the system scheduler works more or less in equal approach, just because this particular application has more threads in total, they have more share of time regarding to all other threads here. For example, if I have 1000 threads and Google Chromium has only 1 thread, then it will get approximately 1,000th part of entire time. But if it creates 10 threads, it gets approximately 10 out of 1010. But if this is large and this is relatively small, you can say it's now approximately 10 out of 1000. And if it adds 100, it knows 100 out of 1000. So it gets more and more bigger share of these time slices for a particular application. And that's also what's happening inside our application. There are many threads working pseudo concurrently in my computer, and if I create only 4 threads, the total slice of time is smaller. If I create 8 threads, they get bigger slice of time in total, and so it works faster. And of course, when I increase it so many times, the biggest part of these threads will be just my application. Nothing will improve because my hardware is the same. But with such artificial creation of threads, actually may make your application faster until all other applications start making these many concurrent threads. Because of course they cannot make your hardware faster, but they may get faster on uz citu rēķina, how it's in English, by stealing time from other applications. And similarly, Google Chrome is very famous with creating many concurrent connections through the network. Again, if you have some router here, again, if it has many concurrent connections, it tries to deal with these connections with more or less fair approach. So these are just processed in sequence. But if some of applications artificially create large amount of concurrent connections like Google Chrome, then of course it gets bigger share of entire resources through this router regarding to other concurrent connections, other applications. And then of course it works a little bit faster. But as soon as every application starts doing this, nothing becomes faster because it just added more complexity for these particular threads or connections in this case. So that's about arms race, and until your arms race gives you some noticeable improvements in slice of time given to your system, you can improve it a little bit. For example, in theory, I should get approximately 2 times faster it using just 2 concurrent threads. In practice it actually is 2 times. So here theory and practice is very close each to other. And now it's even faster than 2 times. But in practice it may be slower. And you may do some tuning here by stealing shared time from other threads inside your computer. But I think that on my computer currently 8 threads are somewhat close to optimum to get best performance. Not all the time. Okay, I will leave it here. So that's about this particular exercise. Do you have any questions or comments?